Hi people, I've got here some Mentos sweets floating in water. So I'm going to use my qi to bring the Mentos down. I'm going to bring the Mentos down using my qi. Okay, oh yeah, relax. So I allow it to float back up. Now my qi again, use my qi. Oh, see, it's going down, it's very tiring to exert my qi. Okay, one more time. Use my qi, bring it down. Alright, so what's happening here? Alright, answer time. So the secret is, well, if you notice, I give the bottle a squeeze. So when I give it a squeeze, it goes down. When I stop squeezing it, it goes back up, right? Squeeze and it goes down. Stop squeezing and it goes back up. Does that answer anything at all? Does that explain anything at all? Not really, right? So how does squeezing cause it to go down? So let's think about it. So before, when it was floating, it must be because the weight is equals to the upthrust, right? So when it sinks, it must be because the weight is now larger than the upthrust. So what do you think? Has the weight increased or has the upthrust decreased? Now obviously the weight of the Mentos sweet cannot change simply because I squeeze it, right? So it must be because the upthrust has decreased. Now what is upthrust? Rho VG. So which term do you think has decreased? Rho, V or G? Do you think that by squeezing the bottle I've decreased the acceleration of free fall? No, right? I'm not so powerful, you know. What about the density? Do you think I decreased the density of water by squeezing it? That sounds like nonsense, right? Anyway, water is quite incompressible, alright? So I don't think I'm so strong that I can change the density of water. So it must be the volume. What's that volume specifically? It is the volume of displaced fluid, right? So by squeezing it, the Mentos sweet displays less water. Now I want you to look at the Mentos packaging. So when I squeeze it, do you notice something happens? Right? So squeeze. Yep, do you notice that the packet like strings whenever I squeeze it? So it's true, when I squeeze the bottle, somehow the packet strings and therefore displaces less water than before. So the upthrust decreases and that's why it sinks. But how does squeezing it cause the packet to string? Alright, so actually there's a pocket of air trapped at the top of the bottle here, right? There's a packet of air here. Okay, I think I'll just pour more water out so that I can show you more clearly. Alright, so I pour away some water. So you see the water is here. So notice what happens when I squeeze the bottle. Do you see the water level rising? Yeah, when I squeeze the bottle, I narrows the cross-sectional area. So the water has to rise up further. But if there's no cap here, then the sweet will just float up with the water, right? It will just float up with the water. But if I put a cap on there, then I have trapped air right at the top here. Those air is trapped there. So when I squeeze and the water rises up, the pressure here will build up. And that will cause the pressure inside the bottle to increase everywhere. Now remember, the pressure at any level is not just H rho G. It's H rho G plus the air pressure above the water surface. So now it's something like atmospheric pressure plus H rho G. But when I squeeze the bottle, the water level rises, the air becomes pressurized. So it's larger than atmospheric pressure now, and therefore the pressure everywhere in the bottle is now higher than before. And this higher pressure will squeeze in the packet, right? Because the packet also contains air inside. So it will get squeezed in, its volume shrinks, so now it displaces less water, less upthrust now, that's why it sinks. Get it? Okay, ta-ta!